Welcome to our channel for probability and statistics. In this video, we will talk about moments and moment-generating functions in statistics. So what is a moment? The obvious purpose of the moment and moment-generating function is in determining moments of random variables. And very important that moment-generating functions can contribute to establish distributions of any functions of random variables. So we called as moment of the random variables about a region is the expectation of random variables as power. So XR, then we take E, expectation or mean value of these functions of random variable. So this is called as moment of random variable X. So if X is a discrete random variable, so we just sigma odd probability of X then times X as power for each different X value. And if X is continuous, then we take the integral from all available region for the X dx with the function X as power times the probability density function of X. So this is called moments as moments about a region of random variable X. So because the first and second moments about a region can be written as the first moment is EX and second moment of X is E expectation of X squared, right, from the definition. So we can write the mean of random variable X actually equals the first moment. And the variance of random variable X equals the second moment minus the means square. Because here second moment is EX square, right? So from the variance has a feature equals EX square minus EX square, right? So EX is mu, so mu square is mu square. And EX square is second moment. So the first moment is the mean value of random variable X and second moment minus the mean square equals variance of random variable X. This applies for any random variable. So although the moments of a random variable can be determined directly from the definition we have seen before, and alternative procedure exists, and this procedure requires to utilize a moment-generating function. So from moment we can also find expression called a moment-generating function of random variable X, and this is the expectation of E is a scalar E 2.718, right? E is Tx in power. So this expression also can denote by mxt. This is the moment generating function of random variable X. So if X is a discrete random variable, its moment generating function of T is ETx in power times probability density function for odd X variable, then take sigma. So this gets the expectation of ETx. And for X is continuous random variable, we can also ETx times the density function fx, then take the integral dx of odd available value of X. So the expectation of ETx in power is called moment generating function of the random variable x. So next page we will show why this function is called a moment generating function. So moment generating function will exist only if the sum or integral of the definition converges. So if a moment generating function of a random variable x does exist, so it can be used to generate all the moments of such a variable. So this is very interesting. If the moment generating function we have seen the previous page exists, then we can use this function to generate all the moments. So all the r's power moments, first moments, second moments, third moments, and so on of this random variable. And the formula for generating moments from moment generating function is like this. So if x is a random variable with moment generating function mxt equals the expectation of etx, right? So we can use this moment generating function, take the derivative with respect to t over r's time, then we can get the r's moment of this random variable if we take the t equals 0 after derivative. So for example, if we want to get the first moment of random variable x, then we just take this function derivative with respect to t one time. Then we set t equals 0 after this calculation, then get the first moment. And if we want to get the second moment of random variable x, then we just take moment generating function and take derivative 2 times with respect to t. Then set t equals 0 after this calculation, then we get second moments of random variable x, right? So we take a look at that example to see how moment generating function can be used concretely in finding the mu and variance. So the question in this example is, find the moment generating function of the binomial random variable x and then use it to verify that mu equals np and sigma square variance equals npq. So from the definition of the moment generating function, mxt equals the mean value of etx of this random variable. So because this is a discrete random variable, we can take a sigma from x to n, all possible random variables value x, then times between etx and the probability function of this random variable. This is a binomial, so we can write the cnx times px times qn minus x. So this expression production take all values from x to x0 to n integer, then we can get the moment generating function. Then we combine p and etx together, and we get a p etx here. So recognizing this last sum of the binomial expansion of ptx plus q is n power. So this part is actually the expansion of binomial of pet plus xq, right? Then we can get mxt equals this binomial expression, right? So now it is easier. We can get the derivative for the first derivative with respect to t from this moment generating function. The result is look like this. And the second derivative of t of this moment generating function with respect to t is a little complicate this one. But if we set t equals 0 to the both expression, both results, we can get the first moment of this random variable is MP, and the second moment is this one. So the first moment is also the mean value of this random variable, right? Because we have seen in the previous pages. So the mean value of a binomial random variable is MP. And the variance we have also seen with variance is the second moment minus the mean of this variable, means of this variable's square. So the variance is mu2 quotes second moment minus the square of the mean value, so equals MPQ, right? Thanks for watching.